All right, yeah, so first of all, let me just show you that. So all the exams, you should really focus on the 4 exams that we've done, and they're all there along with the video solutions of them. If you just really want more practice, you can go back and look at the other old exams. Although if there's material on these exams that are not, or excuse me, if there's material that's not on these exams, then that material will not be on the test. But let me explain what I mean by that. Because I take each of these, I told some of y'all this in class as you in the in-class section. I take each of these questions and I'll change them in one way or another. So for example, I'm going to tell you, I took in this question, which is about the standard for time, and I asked you about another standard. What is a standard? So this question is broadly about standards for the SI system, and so you need to know the standards for the SI system. And that's kind of an extreme case, like where I've changed the question, and I've really changed sort of broadly what it means. Or this question, I don't remember if it made it on the final or not, but it gives equations and asks if they're dimensionally correct or not. And I just give you different equations, right? So you have to go through and do the same process that you did in this one, but it's different. So as you're going through the test, just be aware that there'll be different questions. And that should be good because it'll be familiar to you, but it might be overly familiar, especially if you've worked through these, some of you 5 or 6 times maybe. Then you might just be sort of knee-jerk reaction to some of these questions. But be careful because some of them they will all be changed in one way or another. Okay? In cases where I've just changed one word, but it changes the meaning of the question a lot, I bolded and highlighted and tried to draw attention to that word so that you don't just go right over it. Okay? You have any questions about the format? Abby? They will come from the old text. So for example, let's look at one. What was a good conceptual question? So like, for example, this one came from some of your concept tests, right? Where you had to interpret this position versus time and give the B versus C. So I changed the shape of the graph, right? So maybe instead of being like that, it's like this, or there are like 3 or 4 different scenarios. So in that case, like if you find it helpful to go back and look at the concept test, then by all means do so. Like if you're just sort of struggling with that idea, in the concept test, we went through a number of different scenarios. Okay, as well as in the notes, we did that. So yeah, it might be useful if you're just struggling with a topic for you to go back and look at the notes or the homework questions or the concept test that we did in class. Does that answer your question? Okay.
Like, okay, what if you know this has been changed in the graph, but what about like the word?
Yeah, so let's find another one. So, it's a good one. Let me look at some of the others. Let's look at exam 4, actually. So, by the way, the clock, like a lot of people didn't get, that was one of the student submitted questions. Remember I told you I could submit questions so a student submitted that question for extra credit. So like, for example, here, an object begins at rest, rotate with constant angular acceleration, what is its angular velocity after time at t? Then I could change that now to what is its angular displacement, for example. And then the answer becomes different, right? Because velocity is directly proportional to time, but displacement is a quadratic relationship. So in half t, I go through 1/4 theta. So that sort of thing in the conceptual, like how I change the conceptual questions. Does that answer your question? Yeah, so like I change just one word and it changes the answer drastically. Okay. There are 48 questions. That's a little less than twice the total number of questions, but you have twice the time. So I don't expect time to be an issue. Alright, normally in a help session I'd go through all the topics that we would have on that exam, but since we're going to have every topic on this exam, we're really unable to do that. But what are your questions? Are topics that you would like for me to expand on and go over? What's that, Jake?
A lot of tests for
okay.
A lot of Pascal's pressures kind of messed up my life.
Okay, the chapter 8 or whatever it was, 7. The fluids and stuff.
Like 19 and all that. I had trouble with that question a lot.
Okay. Let me get rid of. I get rid of this.
Yeah, I see.
And then like
Oh no, that's not what I want.
They're not.
Hold on, let me. Why don't I get rid of this thing over here?
That little X on the top, right?
No, that gets rid of the thing.
Oh, yeah. We don't remember X because that's a lot. You want to explain something first?
Well, I'll just keep it. All right, so what about the fluids exactly, Jake?
I mean, if you can just explain question 19.
Okay.
Pretty much.
Yeah. So remember with fluids, we had a lot of different topics, right? We had Pascal's principle, Archimedes' principle, the Bernoulli's principle. We had the continuity equation. We had pressure measurements. We had density, and we had stress and strain, right? Young's modulus type problems. So in those, really, it's a matter of knowing the equation to use and then plugging in the appropriate things. So here, where we had a hydraulic lift, that's going to use Pascal's principle. Pascal's principle, remember, said that anytime you feel a change in pressure in a fluid, then you'll feel that change in pressure throughout. So here we would say the pressure at one point, P1, is equal to the pressure at another point. So any pressure I feel here, I'll feel all the way throughout here. Likewise, I'll feel it over here. So that P1 is F1 over A1 is equal to F2 over A2. That's my definition of pressure, is force over unit area. F1 is given, it's 100 newtons. A1 is 0.01. It's 100 newtons over 0.01 meters squared. And then F2, which is what I want to know, and A2 is 1. So if I solve that for F2, hey Penny, it's, let's see, 100 times 100. F2 is equal to 1, 0, should be 10,000 newtons. Yeah, so B is the right answer for that one. All right, y'all follow me on Pascal's principle? What else in that chapter, what particular principles were difficult? I'm going to go through and look at the questions. 15, sure. Okay, this was conservation of angular momentum, and it says that the way I know that this is a conservation of angular momentum, instead of, say, a torque problem, is because there's no mention of forces here. Okay, anytime we have a torque problem, I'm going to tell you there's a force acting at a certain moment arm. And in this case, there are no forces mentioned, and instead I have two objects that are coming together, two objects with different moments of inertia, and I want to know when they come together, what is their new angular momentum, or what is their new speed. So I have a bar and a flywheel. So initially I have a bar. It has a moment of inertia equal to 2 and an angular speed of 3 revolutions per second. And then I combine that with a flywheel or a disc. So I take my bar and I connect it to the flywheel. So now these two things are rotating at the same speed. They become engaged together, like through a gear or whatever, however you want to think about them connecting together. And they're going to rotate at a new speed. So my new moment of inertia is going to be the moment of inertia of the bar and the moment of inertia of the flywheel. So it's going to be 6 kilogram meters squared. I have these two objects coming together, and they're going to have a new moment of inertia of 6 kilogram meters squared. Because remember, when I have two objects that are coming together, to find their total moment of inertia, I just add them together. Y'all follow me on that? So say I had a disc, and then I have a bar overlaid upon it. To find the moment of inertia, I just add them together. That's like in that Richard Pryor flick, right, that we watched, the clip with the Richard Pryor scene, right? You have the hoop, and then you have the cylinder rotating about a central axis. Y'all remember that? Okay. So, I say my initial moment of inertia, or excuse me, my initial angular momentum, which is pi, or not pi, I'm sorry. We're dealing with angular momentum, so it's Li is equal to Lf. That's I initial, omega initial equals I final, omega final. This is my I initial, 2 kilogram meters squared. Omega initial is 3 revolutions per second. I final is 6 kilogram meters squared. And omega final, I'm solving for, is going to be 1 revolution per second. 2 times 3 is 6. That's equal to 6 times omega, which has to be 1. Okay, that's a good question. I tried to pull questions from all the various topics that we've had. So if you had several questions for a given topic, then you're probably not going to see all of those. But there weren't that many for angular momentum in this test. So probably pretty good bet that you'll see this. I don't know right off if it is, but it's a pretty good bet. Okay, what else, y'all? Unclear?
13.
Number 13? Okay, so here you had to find the net torque. So for example, on something like this, I could give you a different shape. Like instead of a bar, I could give you a hoop or a cylinder or a sphere and have different forces that are acting upon it, and then you can find the net torque. It's the same scenario, and we did something like that in class, but like if instead I made this a disc like this that was rotating about this point, then there would only be 2 forces that would cause torques, right? Y'all follow me on this? And you would have to know which one causes a negative torque and which one causes a positive torque. Y'all follow me on this, what I'm saying? Alright, so like for example here, this would cause on this wheel, or on the bar, a clockwise or counterclockwise torque. Clockwise, it makes it rotate in that direction. This one causes it to rotate in that direction, so this is a counterclockwise. Bar, disc, hoop, doesn't really matter what it is. It's still going to cause those torques. I'm going to get rid of this. So what I'm saying is just be prepared to have different shapes, not just bars and stuff like that. Did y'all hear me? Yeah, you're going to on the test tomorrow. So here I have a negative torque, and here I have a positive torque. This one's clockwise, this one's counterclockwise. Oh, and then also, actually, no, I'm sorry. I was thinking about the hoop. Over here, I have no torque, right? Because I'm rotating at this point, and so R equals 0 for that, so I have no torque at all. What about this force right here? Positive or negative torque? That's a positive torque because it's counterclockwise. I'll call this torque 1, I'll call that torque 2. And then to find the magnitude of the torque, once you've identified if it's positive or negative, you just add them up, right? And I find torque 1 is going to be Fr sine theta. That's 10 newtons times 2 meters times the sine of 30. And then this one is going to be 5 newtons times 4 meters. Let's see, what was the answer? Oh yeah, because sine of 30 is a half, so this is equal to 10 newton meters, and then this is equal to 20 newton meters, and I'll just add them up, and that gives me the total torque. Does that make sense? Yeah. All right. I would certainly expect to see problems like that. Basically, honestly, every type of problem is like that. Gotcha. Okay, so let's say, for example, I can erase all this, y'all? Alright, so let's say that I have a hoop. I'm just going to overlay it here, and let's say it's rotating about this axis, right? And then I can find my net torque. If it's rotating about this axis, this force doesn't do anything to it, doesn't cause it to rotate. This one causes a counterclockwise rotation. So this force causes a positive torque, and this force causes a negative torque, because the torque on the left causes it to go clockwise. And I can figure out what is the torque for each of these. I have 5 newtons times its moment arm, which is 2 meters. That's the distance from the axis of rotation out to where the force is applied. And then this torque is equal to 20 newtons times 2 meters. Of course, it's negative. So this torque is equal to negative 40 newton meters, whereas this torque is equal to positive 10 newton meters. So the net torque will be 30 newton meters in the clockwise direction. Negative 40 plus 10 is negative 30, and so that's going to give me a 30 newton meter clockwise rotation, or torque. Is that clear, Abby? And then all the same business about, like in the next problem where you have to find, what is the angular acceleration, what is the angular velocity after a certain amount of time, all that jazz. Okay? What else? Number 8. We'll go through all the exams, so once we get through with this one, we'll go over to the next one. Yeah. Okay, so a couple things when you saw this problem that should have keyed you into the right answer. First of all, it doesn't say angular acceleration, okay? But if it was asking for angular acceleration, the answer would be 0, right? Because this object is moving at a constant angular speed of 5 revolutions per second. So the angular acceleration is 0 because it's moving at a constant angular speed. However, it does have an acceleration, and we call that our centripetal acceleration. So what we're looking for here is the centripetal acceleration, AR, and this was equal to v squared over r, which is also equal to, if you remember, omega squared r. So that's probably the easier way, is to go through our omega squared r. But then there was one other thing that you had to realize, is that this was given in revolutions per second, and you need that to be in radians per second. So 5 revolutions per second, because radians is our SI unit. Remember, never go wrong converting to SI units. We don't always have to convert to SI units, but you never go wrong doing that. So 1 revolution, 2 pi radians. So that is 10 pi radians per second. All right, so my centripetal acceleration is equal to 10 pi radians per second squared times my radius, which is 0.1. All right, so that's 100 pi squared times 0.1. 0.1 times 100 is 10 pi squared. So E is the right answer. Another thing, by the way, that would have keyed you in that we're looking for a centripetal acceleration is by the units here. They're in meters per second squared. Whereas if it were an angular acceleration, they'd be in radians per second squared. So several pitfalls there for you to mess up, right? Lots of things that you could do wrong. You could not convert your revolutions per second to radians per second. And if you're looking for an angular acceleration, you just sort of left scratching your head, because the angular acceleration is 0. Okay. You could find v if you wanted. Like if you didn't want to follow this, you could say v is equal to omega. Oh wait, no. Yeah, you could say v is equal to omega r, and then that adds in another step. You would take this 10 pi radians per second, and then multiply it times r, which is 0.1, and then that would give you your velocity in meters per second. So that's just an added complication. Okay? All right, what else, y'all? Just stop me if you have a question, okay? Or if you want me to slow down a little bit. What else from this test? Okay, Abby. Absolutely. Yeah, so here we're looking at a set of discrete particles. I know that it's a set of discrete particles because I call them particles, and I don't know, they're not like a bar or a sphere or whatever. I don't give any dimensions for the particles. And the reason that we leave off the one at the top is because for a discrete set of particles, I, the moment of inertia, is equal to the sum of mr squared. And for this particle, r is equal to 0. All right, for these particles, r is equal to 4. It was 8 meters here, right? Yeah. And r was equal to 4. This should have said 8 up there. Right, so the reason that this doesn't add anything to the moment of inertia is because it lies along the axis of rotation. Okay? So R is equal to 0. And so if you added it in here, it wouldn't affect it. Good question. What else? Chapter 4. I mean, exam 4. Kinematics problems, you'll have those, everything you'll have. I've just, where I've had multiple questions, I've taken some out. Multiple questions about a single topic, I've taken some of those out. All right. Any questions about exam 4? Yep. Jake? Okay, well, we can come back to exam 4, but let's look at exam 1 now. Go back to exam 1, and this was on sort of chapter 1, units, SI system, dimensional analysis, conversion of units, basic trig, displacement, velocity, and acceleration, interpreting graphs, which obviously you'll have to do. There is a question where you have a graph like this, and you have to interpret various things. These sorts of things where you have to interpret qualitatively, you'll certainly have to do that. Just some basic calculations like this. Interpreting a graph like this one, a velocity versus time graph, a couple of things where you find the acceleration at a given time. That's going to be the slope at a given time, the slope of the tangent line. Make sure you're up on that. And then finding the distance traveled is the area under the graph. Okay? Let me tell you one thing that might help you. Let's say instead I have a graph, a v versus t graph that looks like that. And then if I want to know, say, the distance that it travels, say, from this time, what does it mean to find the area under the curve? If I'm finding the distance traveled from this time to this time, what area do I find? Is it this area that I find? No. Right, between the origin, it's instead, it doesn't mean anything to find that area. Yeah, that would be a negative distance. You're actually looking then for this area, which will tell you the distance traveled from this point in time to this point in time. Any particular questions about this as I go through?
I did. No, that wasn't my question.
Okay. As I told y'all in class, on the final, you won't have one like this one, number 21, where you have to substitute one equation into another. Because the algebra gets a little complicated. No, will not, right? Okay. Yeah, Jessica?
So, our equation sheet will only be basically what was on test 3 and 4.
Right. The ones that you have there. Yeah.
Can you put interpretations of like graphs?
Yeah, sure. Yeah, absolutely. So, yeah, you'll certainly see that. I think that's pretty important. All right. So let's just say I have a position versus time, x versus t. I don't know. How about that one? You want to ask yourself, what is the sign of the velocity, and what is it doing? Is it increasing or decreasing? So the velocity of a position versus time is the slope. So I look at the slope. The slope over here is big and positive or negative? Negative, right. And there it's negative. It's big and negative, and then it gets smaller and negative. So if I were to draw the v versus t graph, I know that it's going to be down in this portion. It's going to start out big or small? Big. So it's going to start here and go here. So my v versus t graph would look like that. All right, let's do another. This is what you mean, right, Montana? Huh? Yeah, I mean, there are only four different scenarios. concave up, concave down, and then flip that. Yeah, there are 4 different scenarios, but it's hard to memorize those when you're trying to memorize 50,000 other things, right? So you just need to know the process. What was that one that I did? Okay, yeah, so how about this one? Positive or negative velocity in this case? Positive velocity, it's always positive. Wait, no, is that right? No, it's always negative, excuse me. Here, it's small and negative, and here, it's big and negative. So it starts here, and it goes here. Let's do a positive one now. Like this. This one has a positive velocity. It's small and positive, big and positive. Small and positive, big and positive. It looks like that. Is that clear, Montana, everybody? You'll certainly see one of these. Okay? Can I take this away? All right. What else? Number 19. Okay. By the way, you know, if you see one of these like this, I don't know if you will or not, but if you do see, you can work that by energy, which is a lot easier, right? You can say the potential energy equals the kinetic energy, and then it becomes a lot easier to work. And that's certain. You can do it by kinematics, where you have to find the time, and then you find the displacement, but it's a lot easier by energy methods. 19, this one. Who has this? Yeah, Jordan. All right, so here you want to know the velocity versus time graph. Estimate the acceleration at t equal 4 seconds. So this is at t equal 4 seconds. It's sort of tricky. You got to draw the tangent line. Let's see if I can get it. Tangent line, that might not be exactly right, but you'll be able to select out the right answer. First of all, the slope of that tangent line is negative, so that gets rid of that answer. Was C net? I think that's positive, isn't it? C? Is C positive? So that gets rid of 2 of the answers. And then I want to figure out what is the slope of this. I do my rise over my run. I'm going to use these 2 points. Do a triangle. This is 8 minus 4, so I have a rise of 4. 3.5 to 4.5 over 1. Was the answer E on this one? Yeah, so I get negative 4, but you know, it's kind of tricky to draw the right tangent line, so you just pick the closest one. All right, and actually, as I look at it, I probably want to make that line a little steeper, but you'll select out the right one. I try to make the answers different enough so that it's obvious. Is that clear? Be prepared to do something like that, either for that or for a graph. You know, this is easier. A graph that's linear, something like that. And there's another question similar to that. All right? Go on. Yeah, that's right.
You said you picked the closest line, closest to what?
Oh, the answer. So on that tangent line that I drew, looks something like this. I found that the slope was equal to negative 4, and the one that's closest to that is negative 5. Because it sort of depends how you draw your tangent line. When I get the answer, though, I actually do a fit to it, and so I get the actual velocity at that point. So the correct tangent line is of a slope of negative 5, but it's a matter of drawing that correctly. All right. Now, what else? This test. On this one, what happens to the distance between these 2 rocks as they fall? I drop one rock, and then after it falls 4 meters, I drop a second rock. What happens to the distance between them? It stays the same, right? They always, since they're falling at the same acceleration, and they both have the same initial velocity, you drop one and it drops 4 meters, and then they're going to fall at the same, with the same distance between them. Did you hear what I said? Okay. All right. What else? Anything from this test? You good? If you have questions, we'll have some time at the end. We can come back to it. Let's go to exam 2 now. See a vector question like this. It'll probably look a lot like this, but you know the vectors will be changed. Excuse me. vectors will be changed. Maybe instead of a minus b, it could say a plus b, or a minus, or b minus a, or something like that. So make sure you're able to do that graphical part of vector addition, as well as adding up vectors numerically. A lot of people miss number 4. Can I show y'all? Yeah. You missed it, Holly?
Well, I have a question. Why use the limits of like the square root of 10 squared plus 10 squared? Just this word.
Oh, let me just show you. Yeah, a lot of people miss it. So if you missed it, you're in good company. So I have a cannonball, and it goes like that. And then after 1 second, let's say after 1 second, it's roughly right here. I want to know what is its speed. All right, the key term here is speed. That means I want to know the magnitude of its velocity. All right, and its velocity has 2 components. It has a component in that direction and a component in that direction. Now over here, the component in this direction was 10 meters per second. And I know that since the acceleration in the x direction is 0, that doesn't change. So over here, that's what you were going to say, Jake? It doesn't change, right? It's still 10 meters per second. And then right here, after 1 second, since it's accelerating at 10 meters per second squared, I know just right off that my velocity here is 10 meters per second. But if you're uncertain about that, you go back to your kinematics equations, v equals v naught plus at. I'm looking at the y components here. This is 0 plus negative 10. That's my acceleration due to gravity, times 1 second, or negative 10 meters per second. So over there, my velocity is negative 10. So now my speed then is the sum of these 2 vectors, which is going to be the square root of 10 squared plus 10 squared. That's square root of 200, what was it, 14? Yeah, which is 14, roughly.
So that I can go down in y directions and not because of the acceleration of gravity, but because of the 1 second meters.
Oh, no, because of the acceleration due to gravity. Yeah, this right here is that acceleration due to gravity, 10 meters per second squared. But if something is accelerating at a rate of 10 meters per second, then after 1 second, it's going to be going 10 meters per second. 20 meters per second. After 3 seconds, 30 meters. Every second, it gains 10 meters per second. All right? Similarly, you can do a similar thing where what is the distance from this point to this point, in which case you would need to find the distance that it traveled, right? So this distance at 10 meters per second after 1 second is 10 meters. And this distance, you would also need to find y is equal to v naught yt, which is 0, plus 1/2 ayt squared. So that's equal to 5 meters. Right? So you do the square root of 10 squared plus 5 squared, whatever that is, 100 plus 25. No, it's not 14. It's, I don't know what that is. Square root of 125. Whatever that is. Okay? All right? All right, what else from this test? Number 8. Okay, good basic projectile motion problem. I'm pretty sure. Like, the way I do these is I change basically all the problems, and then I'll go back, and it's too long then, right? It's like 60-odd questions, and then I'll get rid of some questions. So, but this one I'm pretty sure is in there. So I have a cannon, fires from a ground level. And then another thing, I asked here for the horizontal distance. I could ask for other things. I could ask for the vertical distance. What is the maximum height it reaches? I could also ask for what is the time that it's in the air. Various things for these projectile motion problems that you could ask. So here I have 1,000 meters per second. That means that the velocity in the y direction has several components, or a couple components. This is 1,000 sine of 30, which is 500 meters per second. This is 1,000 cosine of 30, which is 860 meters per second. All right, so those are my components of my initial velocity. Here I want to know the horizontal distance. I know from my kinematics equations that x is equal to vx times t. I already have my vx right here. It's 860. So I need to know what is the total time in the air. In order to do that, I consider the top of the trajectory, and I say that vy at the top equals 0. And then I can say v top equals v naught y plus ay t top. And then I'm going to solve that for t top. We always use that trick that at the top, the velocity in the y direction goes to 0 to find our total time. Or actually, when I solve for t top, that's going to be 1/2 the total time, because it's 1/2 the trajectory. And then I solve this for t top. It's 0 equals 500, thank you, minus 10 t top. It's 500 over 10, so t top equals 50 seconds. That means the total time is equal to 100 seconds. So that's 860 meters per second times 100 seconds gives me 86,000 meters. I don't know why I put 87. Did we round off somewhere? Oh, I know. I think maybe over here. If I carry 867 or 866, yeah. Okay. But again, different things that I could ask, and I'm pretty sure you're going to see this tomorrow, but I could ask, what is the vertical height? Y? Which is pretty easy because I know the time at that point. So I can just say y equals v naught y t. But here I'm going to use t top plus 1/2 ay t top squared, and then that'll give me the y displacement. Or I could ask you to find the time. We did that over here, 100 seconds. I could potentially ask you what is the velocity over here, or what is the speed at that point. But that's pretty simple, right? The speed at the bottom over here is the same as it was over here. Could ask you the x and y components of the velocity. Those are all pretty low-hanging fruit. But you'd be okay with that, right? But certainly projectile motion tomorrow. 1 or 2 questions on projectile motion. Take this away, y'all? Yes? Okay. What you will not see tomorrow, where was that question that everybody missed, is number 11. So you won't see that tomorrow at all. You get it now. It's a good question. I like it. But
And everybody could be putting money on it.
I don't remember what people put. Yeah, it was a little confusing because some people thought I was talking about this distance. But really I was talking about this distance, these distances. Alright. What else, y'all? I like question. Okay, what is it? 5, Denny. The shortest amount of time is C, right. Yeah, the lower it is in the air, that means that you have less hang time. So how high it goes completely governs what is the time in the air. If it's low, it's not in the air very long. If it's high, it's in the air for a really long time. But obviously that doesn't dictate the range. Right, just because you're in the air for a really long time doesn't mean you go a really long ways. Because like A is in the air the longest, but it's also the shortest. Okay?
You do 18.
Absolutely. Not who asked that? Tesha? Not gonna see that. That's also another question. Like a lot of people miss. I didn't put it on there. It was on the concept test. 18. Do you want me to still work through it?
Yeah.
Okay, I'll still work because it's important, but you're not going to see this question in any way on the test. So here I had a force acting on a mass, and when I have that force acting on that mass, I get an acceleration of 1 meter per second squared. When I have the same force acting on another mass, I get 3 meters per second squared. That means that that mass has to be 1/3 of the original mass. Okay? Because 1/3 of 3, it gets rid of that. And still makes those equations the same. And then it asks, well, if I have that same force acting on both of these masses, all right, so I have this mass and this mass, which is 4/3 of the total mass, right? Because I have 3/3 m and 1/3 m. Add those together. Putting the two masses combined gives me 4/3 of the original mass. Then what is my acceleration? Well, originally it was 1, but now it has to be 3/4 of that. 3/4 of 1 meter per second squared, which was d. We had a concept test question like that. I think it was like 3/2 and 2/3 kind of thing, but you're not going to see that. A lot of people miss that question. Okay? Yeah. Okay, good inclined plane. You're going to see an inclined plane. It might not be exactly like this, but something similar. Here are a couple of things that you need to note. There's no friction, right? Yeah, so there's no friction. That makes it a little easier. There are a couple of forces that are acting in the x direction. I'm just going to draw those forces in the x direction. So this is my y-axis, and this is my x-axis. I have one force here of a... Okay. Yeah. Did you say 21 and I just wasn't listening?
Yeah.
I just wasn't listening.
But
Sorry.
I
This is a good question, okay? You need to know how to do inclined plane, and then we'll go into number 21. So I have 100 newtons there, and then what is the other force acting in the x direction? Right, the component of the weight. And so that's going to be Fw cosine of 60. All right, so those are my two forces, and then I want to know what is the rate of acceleration. Fw here is 100 newtons. You could have done sine of 30. Yeah, that would have been fine. Right. Mm-hmm. Yeah, I recommend that you use cosine for your x component, but remember on inclined planes to always do 90 minus this. But if you want to do the sine of 30, that's fine. That's okay. It's the same. So I do the sum of my forces equals max, and I'm looking for the rate of acceleration, doing the sum of the forces in the x direction. That's going to be 100 cosine of 60 minus 100 equals m, which is 10 kilograms. What was the answer here? Oh, right, 10 kilograms times a. So this is 50 minus 100 equals 10a. So a is equal to -5. But I'm just looking for the magnitude, so 5 is the right answer. Okay? If you will see inclined plane, it might be helpful to go back and just look at that in these notes or whatever, how we deal with inclined planes. What is the friction? Okay, so we have here a frictional force, mu k equals 0.1, and it wants to know what is the acceleration. That's right? So this was a two-part problem. In order to find the frictional force, you have to know the normal force. So you have to draw all your forces here. I have my weight, Fw, and then I also have my normal force. And the first part was to find your normal force. We also have components of this, F sine of 30 and F cosine of 30. So this is equal to 10. This is equal to 17 newtons. Is that right? Yeah, 17. So I just took the components of this vector right here, so I get rid of it. And then I want to find my normal force. I say the sum of the forces in the y direction equals 0. That's 10. 10 plus the normal force minus the weight equals 0. So Fn equals the weight minus 10, which is equal to 100 minus 10, or 90 newtons. So that was the answer to this one, was finding 90 newtons. A lot of people miss this one, but it's a good question. Okay, I don't remember if it made the test or not, but if it didn't, it maybe should have. So 90 newtons is our normal force. And then, Montana, the question you asked is now, what is the acceleration? Well, I have another force that's acting here, which is our kinetic frictional force. I know that kinetic frictional force is equal to mu k times Fn. So that's 0.1 times 90, or 9 newtons. Go with me on this? Okay, so once you get to that part, then I just have these two forces that are acting, 17 and 9 newtons. So the net force in the x direction is 17 minus 9, or what's that, 8 newtons. And that's equal to mass times acceleration. So 8 newtons equals to 10 kilograms times A. So A is 8 over 10, or 0.8 meters per second squared. Okay. That's a good question. I don't know if it made the test, but like I said, if it didn't, it maybe should have. Okay. I'll take this away. Did that clear it up a little bit for you? It's going to go away. This was the hardest test by far. Maybe not by far, but it was certainly the hardest test, I think. Y'all think so too? That was just a bad day you had, I think, if you didn't. I mean, it wasn't easy, but it wasn't the hardest. But I think this was the hardest. Okay. Make sure you're up on these elevator problems, things moving up and down, accelerating. All right. Any other questions on this one? Go to exam 3. All right, we can come back to it if you need to, but let's go to exam 3. We go past 4. I'm okay saying past 4, but just know you're cutting into my dinner time. Yeah, Bree?
I'm not going to have anywhere, like you had a block that was, so you connected.
No, there weren't any on that test. So like she asked if I have any where I have a block with cables on it. No, if it's not, that sort of thing wasn't on this test, you won't see it on the final. All right, this was I think this was probably the easiest test. Work and energy and momentum. You'll see conservation of energy like this, right? Make sure you know how to do that. I can go back and do that. You might see it like this too, conservation of energy. Conservation of momentum, impulse, like this one, finding the force, finding the new velocity when I have collisions. You need to know energy is a scalar, momentum is a vector. Energy is conserved in only elastic collisions. Momentum is conserved in all collisions. All right. Any particular questions on this exam? Number 17. Okay, this was, we wanted to find the force. You know that you're going to approach this. This is a Newton's second law, basically. F equals delta P over delta T. And you know in this problem that you're going to do it this way because there's only one object. All right, there's not two objects that are colliding with one another. There's only one object. And it has a change in speed, and it's also the only one with time in it. Did we have an equation sheet for this one? We did, right? Yes? Okay, good. So I want to know the magnitude of the force. So I find the change in momentum, which is mvf minus mvi over my change in time. And what always trips up people is finding the appropriate signs for these speeds. I always find it useful to draw a picture. Before, I have negative 6.5. And then after, I have positive 3.5. Right, that's probably, if you got this one wrong, that's probably the mistake that you made. And so that gives me m, which was 0.15 kilograms. I'm going to factor out that m. Vf was 3.5 minus negative 6.5. So that makes it positive divided by delta t, which is 0.1 seconds. So that's 0.15 divided times 10 divided by 0.1, which is 15 newtons. All right. So probably if you got that wrong, it was because of these signs. What else on this test? Number 13. Okay, good. Conservation of energy. In this case, you want to identify what type of energy it has at what points. Similarly, for this other problem over here, number 10, we can look at it too if you want. So for example, here I have elastic potential energy. And then after it leaves the spring, it says it leaves the spring, it only has kinetic energy. All right, that's also true here. It only has kinetic energy. But at that point, it leaves the spring completely, and all that elastic potential energy is put into kinetic energy. So you say 1/2 kx squared is equal to 1/2 mv squared. And I'm looking for v. I'll cancel out those 1/2s. V is kx squared over m. Square root of that. K was 100. X is 10 centimeters, but remember your SI units. 0.1 meters squared divided by m, which was 2. Square root of that. Square root of 1/2. What's square root of 1/2? B? Was it B? D? Oh yeah, D. Yeah. All right, so 0.7. Agree?
Are these, it's only going to have either potential energy or...
Not necessarily, no. Let's look at this other one, okay? I mean, this one, it had potential energy up here, and then down here, it had potential and kinetic energy.
I'm talking about the spring one. Since it's not
Not necessarily, no. I mean, you could have a spring that's oscillating back and forth. Let's say these are its maximum points. So that means it's going back from here to here to here to here. All right, and this is its equilibrium point. This is x equals 0. I could ask you what is its speed at, say, x equal 0.05 meters. You follow what you would do on that? So you would say, I have both potential and kinetic energy there. No potential, right, all kinetic. But if it's in between, it has both potential and kinetic. Is that clear what I mean? Similarly over here, right, I can have potential or kinetic at various points. I could also give it a certain speed up here, like thump it with my finger or whatever, and then it will have kinetic energy at the top as well at the very beginning. Just when you encounter one of these, as you will tomorrow, make sure you just look at it and think about, well, what are my energies at various points in this scenario? Does it have potential or kinetic, or does it have both? Probably at some points it'll only have one of those, and at other points it'll have both of them. Or it might have both at all points. Okay? Can I clear this? All right, what else, y'all? Class did pretty well on this one overall. I know not everybody did, but remember, conservative forces are those forces that do not require contact. So for example, gravity here is a conservative force because it's a field force. Anytime objects come into contact with one another, they lose energy. And conservative forces conserve energy. They do not lose energy. Any questions? Holly? Okay, this one's similar to that other one, where it had the ball bouncing 6.5, 3.5 meters per second. And I want to know its change in momentum. And similarly, as that other problem, if you got it wrong, you probably got the signs wrong. So here I'm just looking for the change in momentum. MVF, that's my final momentum, minus MVI, that's my initial. A change in final minus initial. So it's going to be 0.12 times my final velocity. It depends how you look at this. Let's say initially it has 6 meters per second. Actually, it's a bat, right? So we'll think about it coming in this direction, negative 6 meters per second. And then you hit it with positive 14 meters per second. All right, so VF is 14 minus 0.12 times negative 6 meters per second. All right, so that gets rid of that negative sign. So I have 0.12 times 20, which is 2.4. It's my change in momentum.
Yeah, the question I had was, how did you know the 6 was negative and the 14 was positive?
Doesn't matter. Like if you choose them to be, if you choose them the other direction, you'll just get a negative here and a negative here. And instead of 2.4, you'll get negative 2.4. But it's asking for the magnitude, so you just leave the sign off. All right, good question. All right, I clear this? Any other questions? Number 3, sure. Okay, so power is energy or work over time. My energy is, I have this car. It goes from no energy at all to nothing but kinetic energy. And so it's going to be, my energy is 1/2 mv squared over my time. So I have 1/2 of 1,000, or excuse me, 2,000 kilograms times 0 to 30 meters per second squared divided by 6 seconds. 1,000 times 900. What was it? Was it 150? What was the answer? Yeah, so that's equal to 150 watts. Because I don't have any mention of forces here. I mean, you could find your force, but that would be kind of difficult. You would have to, how would you have to do that? Well, you could find the, how am I going to do it? I could, right? I know my acceleration is 30 over 6, which is 5 meters per second squared. And then that gives me, if my car is accelerating, then that gives me a force of 5 times 2,000 or 10,000 newtons. But then I also have to find the displacement. I could do that. You have to go through your kinematics equations. But largely the answer to your question is, I don't give you a force and I don't give you a displacement. You could find them through your kinematics equations, but I don't give them to you. So probably not the way you're going to work it. But since I do give you the velocity and the mass, the final velocity and the mass, then I can find the kinetic energy. And by that work energy theorem, any work you do is going to convert into energy. Does that answer your question, Holly? Yeah. All right. What else? Yeah. Any other questions? Abby? Sure. If y'all need to go, you're welcome to go. It's help session. You can come and go as you like. But 26. Okay, good conservation momentum problem. I have Gwen and Amy. I say PI is equal to PF. I know this is conservation momentum because there are 2 objects, okay? And they both have initial and final velocities. See you guys. Have a good night, okay? Get some rest tonight. PI, nobody's moving, so my initial momentum is 0. And then my final momentum is equal to the mass of Gwen, 150, times her velocity, I don't know what that is, plus the mass of Amy, which is 50, times her velocity, which is 10. And then I just solve for V. So that's negative 500 over 150 equals V. So that's about 3 and a 3 point something. 3 1/3. It's negative, but we're just looking for the speed, so we just answer it positive. Conservation momentum. We'll certainly have one or two of those. All right, what else? Is that all for now? Okay. Well, get some rest. I think probably the best thing you can do now is get a good night's sleep. Don't go out partying. Don't stay up all night. Y'all don't party anyway, I know. But, it's hard. Good students.